Right up to this point, we've been studying different strategies to find instantaneous rates of change in functions. We're going to continue that discussion, but we're going to look at how we can deal with rates of change with things that are not functions. So let me give you an example. We've got this relationship, x squared plus y squared equals 4. This is the equation of a circle. With radius equal to 2. So it goes up to 2, over here to -2, down here to -2, and so forth. So this is a circle of radius 2, and we can certainly think about rates of change on this graph. I could think about the rate of change here. We draw a tangent line there, see it's decreasing. You can look at a rate of change over here, draw a tangent line there, see that the function's increasing, and so forth. But we have here two different variables in the equation. They're both raised to a power. So how do we figure out rates of change? And where it gets especially interesting is you might have a single x value, say right here, that corresponds with two y values, and they have different rates of change. This one's positive, this one's negative. So how do you determine the instantaneous rate of change? Well, all of the rules we've learned up to this point will be helpful for us. And I will walk us through the strategy to find the rate of change here. So it's called implicit differentiation. I'll write it up here for us. Implicit differentiation. Just remember the word differentiation just means find the derivative. Find the derivative. So we're going to figure out how to find the instantaneous rate of change, the derivative of this. So I'm going to start off by using this derivative operator that just says find the derivative with respect to x. And I'll do that for both sides of the equation. All right, so let's start on the right. That's the easiest part. What is the derivative of a constant? 0. So the right-hand side is going to be 0. I notice that the variable here, x, that I'm taking the derivative with respect to x, and I've got that's the same as this here. So the derivative of this piece is 2x. Now the derivative of y is going to be a little bit trickier. We're going to end up using the chain rule on this, and let me explain why. We suppose that y is some function of x. So that there's some sort of relationship between those two variables, the x and the y. But we're not taking the derivative with respect to y. We're taking the derivative with respect to x. So we'll apply our derivative rules like normal. So the y squared will be 2y. But then we have to multiply that, this is the chain rule idea, by the derivative of y with respect to x. Because we were taking the derivative with respect to x, this was a y. And I'll show you in a moment when we come back over here how that all works. So this is our relationship here so far. Well, I want to find the relationship for the instantaneous rate of change between y and x here, the dy dx. I need to isolate this. So I'll go ahead and subtract 2y times dy dx is equal to -2 over 2x. Then I'll divide both sides by 2y. Well, let's just divide by the 2's first. Those are going to cancel out. And then I'll get dy dx is equal to -x over y. So this instantaneous rate of change depends not only on the x value, it depends on the y value. So let's convince ourselves that this truly makes sense, that this whole strategy actually works. So I'm going to go back over here, and I'm going to solve this for y. So I've got y squared is equal to 4 minus x squared. So I'll begin by taking the square root of both sides. I get y is equal to plus or minus the square root of 4 minus x squared. Let me go ahead and handle the plus or the minus cases separately. So let's work on the plus case first. Y is equal to the square root of 4 minus x squared. That can be rewritten as 4 minus x squared to the 1/2. So dy dx, the derivative of y with respect to x, is equal to, I bring the 1/2 down in front, 4 minus x squared to the negative 1/2 times the derivative of what's inside. This is the chain rule. Derivative of what's inside is in fact negative 2x. Well, I can combine this 1/2 with that negative 2. That becomes negative 1, so I get a negative x. Now, raising something to negative 1/2 is the same as dividing it by that same quantity to the 1/2, so I'll go and write it like that. 4 minus x squared to the 1/2, which is the same as this. So let me go and write that there. Square root of 4 minus x squared. Well, notice 4 minus square root of 4 minus x squared was what our y was, right? So this is the same as negative x all over y. And that matches what we got over here. That was for the positive case. Let's see if it also holds for the negative case. So we've got y, I'll do that y is equal to negative 4 minus x squared to the 1/2. So this is the negative case. So then we take the derivative, so dy dx is equal to negative 1/2 times 4 minus x squared to the negative 1/2 is our dy dx times the derivative of what's inside, which is negative 2. Negative 2x. All right, we can combine these pieces. We end up getting the negative 1/2 times the negative 2x, just leaves us with an x. And then all over here in the denominator, we've got the 4 minus x squared. And that's all underneath the square root. Okay. All right, now in this case, remember our y was negative of this. I've got a positive value here, so this is equivalent to x divided by, this is negative y. Well, that's the same result we got over here. Negative x over y is equivalent to x over negative y. So in either case, we were able to show that we got this result. So we're convinced that this strategy over here, which was much simpler than that strategy over there, was an appropriate strategy by which we could find the derivative here. And in this case, the derivative turned out to be a function of two variables. All right, for this example, we're going to use a cylindrical can as our context. So I'm going to try to sketch this as best I can. No pun intended there on the can. Okay, so we've got the cylindrical can, and we are filling up this can with water. So I'll sketch some water in here. So this is water. So we're filling up this can with water. So water is flowing in here at some rate. I've got some spout up here. The water is flowing into this. Maybe it's a hose or something else. And I want to see how the volume of this is changing, as well as the volume of water comes in here. I want to see how the height is changing. So let's see what the relationship is here. We know that the volume of a cylinder is pi r squared h, where r is the radius here. H is going to represent the height of the water in this can. Let's just go ahead and say that h is measured in centimeters, and also that r is measured in centimeters. The volume, because we've got centimeters times centimeters squared, the volume will be measured in centimeters cubed. And so we've got all those relationships. But let me go ahead and take the derivative of this equation with respect to t, with t being time in seconds. So the derivative of both sides with respect to t. All right. So the derivative of v would be 1, but because we're taking the derivative with respect to t, we're going to have to multiply it by dv dt. So this is just, derivative of this is just 1 times dv dt, or just plain old dv dt. Now let's come to here. Well, we see we've got a constant, so constant multiple rule tells us we can bring down that pi. But then we've got two quantities being multiplied by each other, so we're going to have to use the product rule. So the derivative of the first, well, derivative of r squared is just going to be 2r, but this variable differs from that variable, so we're going to have to use the chain rule and multiply this by the derivative of r with respect to t, or dr dt. Now let's go over here to this next value. So we did the derivative first times the second, which is h, plus the derivative of the second. Well, derivative of h would be 1, but because the h differs from the variable we're differentiating with respect to, we're going to have to multiply it by dh dt. This is the chain rule. And then times the first, which is r squared. All right, let's think about what these things mean. You know, r is our radius. dr dt is the rate of change in the radius with respect to time. dh dt is the rate of change in the height with respect to time. Then r, of course, is the radius again. So this gives us the rate of change of our volume. Let's think about this. Is the radius of the cylindrical can changing? No, it is not. The radius of this remains constant. So what's dr dt going to be? dr dt equals 0 since r is constant, right? The derivative of constant function is 0. So this whole piece is going to drop out. And then we're left with r squared times dh dt. So dv dt is equal to r squared times dh dt. All right, let's make sense of that. The rate of change in the volume, which will be centimeters cubed per second, is equal to the radius squared times the rate of change in the height in centimeters per second. So this is going to be centimeters squared times centimeters per second. We'll get the right units of centimeters cubed per second. So we call this related rates. You're using the implicit differentiation. We've got these two related rates here. The rate of change in the height is directly related to the rate of change in the volume. We are now going to dive into related rates and marginal analysis. Marginal analysis is commonly used in business, where we use the derivative to analyze changes in profit, cost, and also changes in revenue. So I'm going to work an example. I've got a handout that you'll get to work through with 6 problems. I'll work problem number 5 on the board to illustrate how these problems are addressed. So on problem number 5, we're given this. We've got a demand equation, which I'll put on the board here shortly. We know that revenue is a function of price, and we're tasked with finding the marginal revenue. We're tasked with looking at what's happening with revenue over time as price is falling, and then make sense of the data. So I'll kind of dive into that and work through each part of the problem. Let me go ahead and write the demand equation first. We have this relationship is given to us that the quantity sold is equal to 900 minus 30 times the price. So let's make sense of this. If it's free, so the price would be 0, then we would expect 900 to be sold. But as 900 units, that is, 900 units would be sold. As the price goes up, the number of units sold is going to go down. We can see that by the subtraction here. So that's our demand equation. We know revenue is a function of price. So revenue is a function of price. It's just price times the quantity sold. But we know what the quantity sold is here. So I'll just go ahead and write this like this. If we distribute, we get 900p minus 30p squared. So that is our revenue function as a function of price. So the marginal revenue is dr dt. This is the marginal revenue with respect to price. So I'll differentiate this. I'll get 900 minus 60p. Now let's think of what the units are. Now I didn't state the units here, but let me go and state them now. Q is units sold. P is price in dollars per unit, right? Then revenue is going to be in terms of dollars, because if we take price in dollars per unit, multiply by units are going to cancel. It's just going to be revenue in dollars. So let's come over here. We've got the output is revenue in dollars. So revenue in dollars. The input here is price. So price in dollars. So basically, this is the equation that will give us how much revenue we expect to receive as the price changes. So that's DRDP. That was part A we were supposed to find. The next thing we're asked to find is DRDT. So let me go ahead and write that on the board here. So our task is to find DRDT given dp dt equals negative $1.5 per week, and p equals 10. All right, let's make sense of this. So we're supposed to find the rate of change in revenue with respect to time. Up here it was with respect to price. Now it's with respect to time. We're told that the price is changing. It's dropping by $1.50 per week. That's the price per unit. And that the price is currently $10 at whatever point in time we're analyzing this. So we go back to my original equation here, R, as a function of P. And I'll differentiate both sides with respect to t. So I want to take the derivative with respect to t of r, but I also want to take the derivative with respect to t of this equation here, or this expression, 900p minus 30p squared. Of course, the derivative of r with respect to t is drdt. The derivative over here is going to be 900. But because the variable here, p, doesn't match the t, I'm going to have to use the chain rule, times dp dt. I continue on over, the derivative of 30p squared, that's going to be minus the 60p. But once again, p is a function of t here, so I'm going to have to use the chain rule, dp dt. So there is my rate of change in revenue as a function of time. So let me go ahead and plug in these values that was given. So drdt is equal to 900 times the dp dt, which was the negative 1.5, minus 600 times the price, which was 10, times negative 1.5. So that's the multiplication I'm going to do. Now I can do this I'm sorry, I did a typo here. This is 60 times P, not 600, so 60 times P. There we go. Altogether, that's 600. That'll be 600 times the negative 1.5. Here I've got a 900 times the negative 1.5. So altogether, it's going to be 900 minus 600, which is 300 times the negative 1.5. That's negative 450 dollars of revenue per the unit of time. Let me double check to see what the unit of time that they specify. It's dollars per week, so this will be per week. All right, so let's make sense of this. When the price is falling by $1.50 per week, and the price is $10, the revenue is going to be falling by $450 per week. And then moving on to part C, it says, is revenue rising or falling at that instant? Well, we just indicated the revenue is falling. That, of course, is we've got price dropping. Even though sales may be increasing, unit sales it is, may not be enough to overcome the decrease in the price. So revenue is falling. All right, that's problem number 5. You guys get to work the other problems. So I wish you much success in that. It's going to be key keeping track of which derivative you're talking about. Here was revenue with respect to price. Here's revenue with respect to time. So you need to pay attention to that. Make sure you're appropriately using the chain rule as needed.